Alright, so this is your video for section 5.5. I'm going to also use this video to review section 5.1 because on the tests the majority of you could not do an LRAM or an RRAM, whichever one I asked. So let's start off with the homework will be chapter 5, number 16, so it should match the 5.5 section. Go ahead and take out your notes packets from chapter 5. We're going to apply the trapezoidal rule, so if you remember I had to keep taking those questions out because we were saving that. We were going to save that section till the end. So just starting off, given that we have a function, we can integrate now to get an exact answer. So for this guy, not the nicest looking problem, but add 1 to the power, which would be third, so 1 over 24 x cubed plus x, and then f of 4 would be 64 over 24 plus 4, and f of 0 would be 0. So we end up with over here, divide by 8, I guess? 8 thirds plus 12 thirds, so 20 thirds. So the answer to this integral will be 20 over 3 minus 0. F of b minus f of a. So 20 thirds. So now I'm just going to ask that you do an LRAM with 4 subintervals. So even though the graph is there, I actually want to go back through how we do it without a graph. I am going to start off by creating the LRAM, so you should still be able to draw a RAM. So we connect to the curve on the left side of the curve. Connect to the curve on the left side of the rectangle I meant. Alright, so there is what the LRAM looks like, and then up here, if I was going to do the LRAM, I want 4 subintervals, so the length of a subinterval, which is delta x, would be b minus a all over how many I want. 4 subintervals, therefore each subinterval is 1 wide. We would start from 0 then, count by ones, up to b. And then if we're doing an LRAM, the one that we skip is going to be the very last one. But the way that we decide that is, first of all, you need to find your deltas, which means these over here would be the width of our rectangle, and your f of x becomes the height of the rectangle. So the width of the first one is 1 minus 0, which is 1. The width of the second one is 2 minus 1, which is 1. The width of the third one is 3 minus 2, which is 1. And the width of the fourth one is 4 minus 3, which is 1. So all of the rectangles have a width of 1. Your heights will help determine which of the y values we're going to use. So I'm just going to write up, I guess, some of them. So that would be 1/8 plus 1, 1/2 plus 1, 9/8 plus 1, and then 4 would be 16, so 2 plus 1. So this is 3, this is 17/8, this is 3/2, this is 9/8. So how do we decide which rectangle or which height we use? So if this is an LRAM, then your first width would be this yellow value, and between the two choices you have, which is 1 and 9/8, the left one would be the first value. So that would be the first rectangle. The second rectangle that we would use would be a width of 1 and a height of 9/8. The next rectangle we would use is a width of 1 and a height of 3/2. And then the last rectangle we would use is a width of 1 and a height of 17/8. And then you'll notice what does not get used is the very last value here. So I wanted to review that because some of you are really struggling with just finding the LRAM. And that was on the last test you took. So your LRAM would be 1 times 1 plus 1 times 9/8, the green, plus the orange, plus the red. Okay? Next, RRAM. So the difference graphically would be, instead of the curve hitting the rectangle on the left side, we want the curve to hit the rectangle on the right side. So your first rectangle would be this high, Your second rectangle would be this high. Your third one would be this high. And then your fourth one would be this high. And again, same thing as before. If I wanted to, and then pretending that this was a brand new problem, my width would end up being 4 minus 0 over 4. Now, this only works for consistent intervals. I should have mentioned that in the LRAM. It only works for these. You could probably get away with not having to do that just by using a little bit of common sense. The type of problems that are a little bit more common would be table problems. So again, I'm just going to rewrite those values from before. I believe 0 was 1. 1 was 9/8. I'm going to have to go back and look real quick. 9/8, 3/2, 17/8. 9/8, 3/2, 17/8. And then the last one I believe was 3. Alright, so pretending that we didn't have a graph, pretending all they gave us was a table, then the first thing you would need to do is find your widths. So your widths are the distances between these numbers. So because this is a common width, that's why these are all 1, because the distance between each of these numbers is just 1. So how do I figure out which y value I use? So again, I'm going to use my highlighter here. The very first width is 1, and if I'm doing an LRAM, between these two numbers, I pick the right side number. The right would be the later y value, so that would be the first. Your second would be the width and this one. Your third would be the width and then this one. And then your fourth would be the width and this guy. So what you'll notice this time, we didn't use this value, the 1. Okay? So my RRAM, would be the pink width of 1 times the 9/8 plus the green width of 1 times 3/2, yellow width of 1 times 17/8, and then orange width of 1 times a height of 3. Matches the graph that's up here. Additionally, the reason why we can take the 1 out is because it's common, and that's how we end up with that formula that looks a little different. The common width on the outside, all the heights on the inside. So what I'm going to show you is, just like I did here, you don't ever have to take out the common width. You could just write literally the step before, this whole step, that had every single width written, and that way you won't make the mistake of trying to pull out a common width even though there isn't one. So, I'm going to create trapezoids now. So my trapezoids, and this thing is huge, so I'm actually going to make it a little smaller. Makes it easier for me to draw. Alright, so my trapezoids, what you're going to do is you're going to create your point. So if we're doing 4 trapezoids, this would be trapezoid number 1, this would be trapezoid number 2, this would be trapezoid number 3, and then this would be trapezoid number 4. So that is where I'm going to create my trapezoids. The way you create them is at each x value, you create the points for the y values, and then you actually just connect. And then the next one I'll do in pink. So at 1 and at 2, I'm just going to connect. And then in brown, 2 and 3, connect. And then in, I guess, no, not blue, light blue, we'll do 3 to 4, connect. And those create each of the trapezoids. There's that one. The brown one was this guy. The pink one was this guy. And then the first one was our red one. So that, you can see, trapezoidal is so far the most accurate. And then we're going to actually use this to create the approximation. So on the next page here, I'm going to check that out. here is my diagram from before, and then we're going to have to understand where the bases of a trapezoid are. You're really used to seeing your trapezoids this way. Parallel, this would be base 1, this would be base 2, and then the height was the weird one where you had to draw in a height. Heights are always going to be perpendicular to the bases. So if you look at our trapezoids, their parallel sides are running up and down. So the trapezoid is laying on its side. So this would be base 1, this would be base 2, and then the height, I'm going to use the same color, goes this way. And then the pink one, if you want to do it again, I'm only going to do it for the first two, that would be base 1, that would be base 2, and then that would be the height. So what you'll notice is that the height of the trapezoid is kind of like the width of the rectangle. It's also that delta x, the change in x's. So what I'm going to do is use the formula here. This is the easiest formula to use. I'm going to take all the heights. So the way I'm going to rewrite this would be delta x over 2 times y1 plus y2. So you know that your height is an x value, but your bases are y values. So the very first trapezoid in red, my first base would be, actually let's do delta x. So delta x would be 1 divided by 2 times the first base, which would be y of 0, plus the second base, which is y of 1. The second trapezoid would be delta x, or a height of the trapezoid of 1 over 2. The 2 is always there. And then y of 1 plus y of 2. And I'm writing it that way because then you would just use the y value at those specific x values. The next one in brown would have been a height of 1. The 2 is always there because that's part of the formula. And then y of 2 plus y of 3. And then the last one in light blue, 1 divided by 2, y of 3 plus y of 4. So what you'll notice, it uses every single y value for a trapezoidal. We don't skip any of them. Things that you also might notice, we use all of the interior heights twice, and then the exterior heights only show up once, and that should make sense. Notice here, we share that wall, we share that wall, we share that wall. That's why that happens. So on the next page here, there's this other rule. These are other rules that other teachers may teach. I am not going to use either of them. I've chosen to just stick with a trapezoidal rule will be the sum of your delta x's divided by 2 times your first y plus your second y. And it'll be the sum of every single trapezoid. Okay? So, other thing that I want to quickly go over is over-under approximation. So, trapezoidals are interesting. We no longer care about just increasing or decreasing. Trapezoidals deal with concavity. So, anywhere along this concave up curve, if I draw a trapezoid, whether it be a big one or a small one, a very tiny one, doesn't matter. Notice that the trapezoid is on top of the curve. Doesn't matter if it's increasing or decreasing. What do I mean by that? If I increase two different ways, increasing this trapezoid is above, but increasing here, oh sorry, that's the decreasing curve, wow. Alright. Increasing this way, the trapezoid is below, and because the trapezoid is one of the times above and one of the times below, that increasing can't be the rule. Hopefully that makes sense to you. So, it's actually the concavity that creates it. So if I look at this guy, if I draw a trapezoid, whether it be a skinny one or a big trapezoid or an extra tiny trapezoid, all those trapezoids are underneath the curve. So for a trapezoidal approximation, your overestimates happen when we're concave up. That would be your second derivative is greater than 0. We're an underestimate when we're concave down. And that would be where your second derivative is less than 0. And then I just wanted to review one more time LRAM, RRAM. So remember, LRAM and RRAM, they are the ones where we just draw increasing or decreasing. So then left rectangle would be this one. Left rectangle would be this guy. So we know we have an over approximation when f is decreasing, and we have an under approximation when f is increasing. So same thing here, RRAM, hitting the rectangle on the right side. We have an over approximation when we're increasing, and an under approximation when it's decreasing, and then hopefully you remember tangent lines. We did those with concavity. A lot to memorize. Draw a tangent. Oopsie, I didn't touch it, but there's one, there's one. Your tangent line is above the curve when we're concave, down, and then we're under the curve when we're concave, up. And notice for every single one of them, I drew. I don't memorize the rule because I'm too afraid that I might get it wrong, so I always draw. All right, so using the trapezoidal rule, with n equal to 4, approximate the value of the integral. Anytime you do that, if they're just telling you n equal to 4, then this is a consistent interval, which means, first of all, from pi, let's see, delta x equals pi minus 0 divided by 4. So I'll count by pi over 4. So my x, my f of x. So I would start at 0, count by pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, and then my y values, the sine of 0 is 0, the sine of pi is 0, the sine of pi over 2 is 1, and the sine of pi over 4 is root 2 over 2, and then this is second quadrant, which is still positive, so still root 2 over 2. So we're going to use the fact that each of these would be my widths. Those would be my delta x's, which is, let's see, let me move that up. My delta x's would be pi over 4. So every single one, how do I know that? Because the distance between each of these is pi over 4, and remember we actually calculated that at the very beginning. And then if we were doing an LRAM, the first rectangle would be this one times this height. If we were doing an RRAM, the first rectangle would be pi over 4 times root 2 over 2, the second height. And then because we're doing a trapezoidal, this would be our y1 and this would be our y2. We would need both for the first trapezoid. So here we go. Trapezoidal rule would be, remember, delta x dividing by 2 means multiplying by a half. So you can do pi over 8. I'm just going to show it here for that first one. So here's my first trapezoid. Height of 0, height 1 of 0, height 2 of root 2 over 2. There's trapezoid 1. My second trapezoid, I'm just going to do it right underneath here. Plus pi, and then this time we can do pi over 8, because pi over 4 divided by 2 would be pi over 8. First height would be this guy. Second height now would be this one. And it matches the brackets that are here. It's a different color, actually. So these brackets would match these brackets, which are height 1 and height 2. So this would be root 2 over 2 plus 1. Next one, I would match this bracket with these heights. So I get pi over 8 because pi over 4 divided by 2. 1 plus root 2 over 2. And then last one, I'll just do that in black. Oh, no, I won't. Just kidding. Pink. Here's the width, which is also the height of the trapezoid. And then here's the last one. So that'd be y1, and then that would be your y2. So pi over 8, pi over 4 divided by 2 is pi over 8. And then root 2 over 2 plus 0. So we used every single height. All right, using the concavity of the function, predict whether the approximation is an overestimate. So it says you can graph it. So we're doing the sine curve from 0 to pi. That would be from 0 to pi. Pi over 2 is 1. So then it's obvious that we're concave down. So because the second derivative is less than 0, concave down, draw one trapezoid. It can be a huge trapezoid. It doesn't actually matter because it's a rule. It doesn't matter if the trapezoid is big or small, it'll follow the rule. Then we know it is an underestimate. So find the integral's exact value. That would be f would be negative cosine of x, f of pi, which would be over here. The cosine value is negative 1, so this becomes positive 1. F of 0, 0 would be here. That cosine value is 1, so that's negative 1. Therefore, you get 1 minus negative 1, which is 2. That's the exact value of the integral. All right, so here is a simple word problem, pretty common. I actually am going to do this two ways. Let's do a trapezoidal, and then we'll also we'll pick one. We'll do an LRAM. So let's start with the trapezoidal. So trapezoidal says that, let me just write out the formula. A trapezoid would be delta x over 2 times y1 plus y2. Okay? So my trapezoid, I'm just going to write each of my trapezoids going down so that we save a little space. So here, that width is 0.5. I'm just going to go through and do all my widths. That width is 0.4. That is 0.6. This one is 0.4. This one is 0.5. And this one is 0.3. So maybe actually we should do the trapezoid over here. So my very first one is 0.5 over 2. Remember, delta x over 2, y1 plus y2. So there's my first width. That's this guy right here. And then y1, y2 would be these y values. My next one, which was 0.7 over 2. My next one would be 675 plus 720, which would be these two. My next one after that was at 0.6. And those y values are 720 and 700. And you can check if you're doing this right, because these should always be the same if you're going in order. Next one is 0.4. And then these two would be 700 and 680. Right? This one is 0.5. Where are we? This guy is 680 and 550. And then the last one here, 0.3. And then last two, 550 and 320. And for those, if you look, I know I did it right because all of my interior y values will match. Add those all up, so do a sum in your calculator, and you would have the trapezoidal approximation. Now what I'm going to do is redo the problem as an, I think I said I'll do an LRAM. Let's do an RRAM. I feel like I do a lot of LRAMs. So an LRAM would say, first, in red would be the width here, which is 0.5. And if I'm doing an RRAM, I can't remember. I keep switching back and forth. I'll write it down so I remember which one. An RRAM, this would be my first height, R1 here. So that would be 0.5 times 675 plus my second rectangle would be the width here, which is 0.7, and then between these two, so this is the reason why it works out that way. This is the left side, this is the right side. It matches where this bracket was, and this is the right side, so that's the second width. So 0.7 times 720. And so now you start to notice that there is a pattern. We would do this width, which is 0.6, and then this one would be the third one. And then just to, I'm going to keep going. 0.4, this would be R4. R4 would be 680. And then the last ones I'm just going to do in the same color. So that width would be 0.5, which would be R5, so 550, plus this would be 0.3, and then this would be R6, 320. And then now that I'm thinking about it, I am a little concerned, so I'm actually going to do an LRAM also, so we'll do all of them here. So this will be my LRAM. What you'll notice for an LRAM, the left side I won't have to change. It'll be this right side of value. So these are the heights of my rectangles. The width of the rectangles for an RRAM, the LRAM, the trapezoidal, they're all the same. It's which heights you use. So the very first one if these are the two values I'm picking between, this would be a left value and this would be a right value. That's why this is our L1. So the very first rectangle would be 0.5 times 0. The second rectangle in blue, because it's going between these values, this would be the left side, and this would be the right side, so this is L2, 675. 0.7 times 675. The third one in orange, between these two, now that we're looking at it this way, this is now the left side, this is the right side, so that's L3. L3 is, in orange, 0.6 times 720. So now you're going to start seeing them match up. I'm going to show you in blue. The left, so this width matched up with this one, this blue one matched up with this guy, this one matches up with this one, and you can now see, physically see which ones you're going to use in order. So 0.6, and then I got 0.4 times 700, then I have 0.5 times 680, and then I have 0.3 times 550. So the values are different than the RRAM, and you'll notice for the LRAM we didn't use this guy, but for the RRAM we didn't use the first one. Okay, so this would be a traditional free response problem. It's just one part of it. It says write an integral expression in terms of T of x for the average temperature. So here is the temperature. They want its average. It's the same. So the formula I'm using for an average temperature would be 1 over b minus a, integral from a to b of temperature. We're still using that. Estimate the average temperature using a trapezoidal sum. Indicate units of measure. So I'm just going to do the indicate units of measure right now. It should make sense. If I ask you for an average temperature, you should know that the answer you're giving me should be a temperature. If you don't know that, the units would be, this would be 1 over b and a are x values, which are centimeters. Integral T of x is this, and dx would be centimeter. So centimeter, centimeter, and we still get left with degrees Celsius. Okay? So we know that the units of measure are done. I'm going to erase this piece right here so I have some space. And what I'm going to do is, using the table that's here, I'm going to create my delta x's here, which would be 1. This one is 4. This one is 1. And this one is 2. I know that using this first one here, this would be my y1 and this would be my y2. Okay, so my trapezoidal, 1 over b minus a. B minus a would be from 8 to 0. And the integral is where I'm going to do my trapezoidal rule. So 1 delta x divided by 2, one more time, delta x divided by 2, y1 plus y2. Okay, times y1, which is 100, plus y2, which is 93. So there's my first one. My second one we'll do in pink is the 4. So this is now my y1. This is now my y2 in pink. So pink would be 4 divided by 2. Y1 is 93. Y2 is 70. In brown, the next one, the width is 1 over 2. Y1 would be the first one here. Y2 would be the second one here. So 70 plus 62. And then the very last one, which I'll do in gray, that would be this guy, which is 2 over 2. And then y1 would be the first one, y2 would be the second. So 62 plus 55. Okay? So then you go back through and you make sure, did you estimate the average? Meaning I would have to go and use my calculator now to find this. Oopsie. And that value would be, I'm just going to actually write them out real quick. Plus, oh, wow, I can't add. I subtracted. That's dumb. All right, so 193 divided by 2. And yes, honestly, I would just use the calculator for this. 163 times 2 in the front. Oopsie, missed that. Next one is 1/2 times 132. And then next one is 55, 1, 11, 7. And then I would add those all up, divide by 8. That would give me the estimate the average. With the trapezoidal, I wrote my integral expression and I indicated the units of measure. There were 3 things it asked me to do. I did all 3 things. All right, that's it. That should be everything. So just a little summary. Remember a trapezoidal rule. We're going to do one trapezoid at a time, delta x over 2 times y1 plus y2, and then you also want to remember the trapezoidal rule, over and under approximations depend upon concavity.